So once again, welcome in this new lecture of nonlinear elasticity course. I just remind you that this is the 13th lecture, so we're progressing lecture 13. Today, the general topic is still about the hyperelasticity. So we're still working on hyperelasticity, and we're still working on refining our understanding of how a constitutive equation should be done. We have reasoned a lot in terms of energy, but what we will do finally today, which finally will put us in the position, will give us the possibility to make calculations. Finally today we will derive constitutive equations. And so finally today, by confining attention to isotropic solids, today we will derive constitutive equations of isotropic solids, and in particular we will see how is the stress related to the gradient of deformation. So insofar we have seen these things in rudder theory, and but now we will do this more in practice. So before passing to the scope of today's lecture, I want to do again introduction, very brief contextualization. Is, if you remember, in the word of hyperelasticity, well, essentially everything comes from the so-called principle of work, and through the principle of work we were able to say that there exists a function w that depends on the deformation, and this function permits to define the components of stress, so that Sij is equal to the derivative of w with respect to the deformation Fji. So this you had already seen this with Michel. Then what we did together during the last week and during the week of yesterday was essentially to show that this function, this strain energy, will not in general depend on 9 functions, but its dependence can be somehow simplified. And how? Well, the first thing is that we introduced the concept of objectivity. Objectivity, once again, it represents the fact that if you superpose rotations, which means you put them after, they should not affect the energy. So this led us to the simplification that the energy will only depend on C. Now what is C? C is the tensor F transpose F, and this tensor has not 9 but 6 components. So C has 6 functions. There was subsequently a second simplification we did, and the second simplification we did in the energy was the idea of isotropy. Now the idea of isotropy led to a further simplification, and I will not go into the details because we did already do this, including a recap in the last lecture, but essentially we arrived to the conclusion that the energy will only depend on, say, the 3 invariants of C. So I1, I2, and I3. And these are the 3 invariants of C, so we already have seen. I would just say that these are the so-called scalar invariants of C. Scalar invariants of C, and the nice thing is that we got to the point that in fact we don't have 9, we don't have 6, but we rather have three functions. So essentially the energy is depending on these functions, and the task of this, the way in which you will actually write this energy is not yet at our disposal, we need to understand. So to find this energy here and to find the form of W, so let me just write to find the specific form of W of I1, I2, I3, we need to conduct experiments. So essentially what we do, well, what type of experiments? Well, there can be a lot. Well, of course, you could say, well, okay, like, how can I understand if this is what is the energy? Well, the only type of experiments that you can do is to take a piece of material. You take, for example, a specimen of material, like a little cube, and then you do some experiments on this cube, yes? So, for example, you stretch the cube. Well, you expect that if you stretch it, then it will thin, it will elongate, and what you can do, so you do a certain deformation, and there will be a certain stress inside of this material, yes? And then you go and you plot, for example, the dependence of stress on deformation, yeah? And then these will go in a certain way, for example, like that. And from this, you do an exercise of curve fitting, and you are able to deduce the form of this W of the various invariants. Now, there is immediately an observation to do. I think this is clear, yes? I mean, the idea is the following. I have a function that depends on the deformation. How do I find it? By fitting. I take a cube of a certain material, I subject it to a certain deformation, there is a stress in the material. The stress, I know it because it's the derivative of this function relative to the deformation very well. I obtain some curve, do some fitting, and get the expression of W. That's the way in which we produce strain energies. So even before starting to give, so you see, the very first thing to do at this point, even before thinking of a specific material or like shooting in the air possible expressions of this W, the thing that we need to do is to find the explicit form in which S depends on F. And this is really the task of this lecture. So in this lecture, the task is to find how S depends on the gradient of deformation for a general W. Okay, so this is really what we will do in this lecture. It will be a little bit technical, but still it will be very important, because if you have to model rubber, or you have to model silicone, or you have to model, I don't know, a fiber reinforced material. Well, it can't be fiber reinforced, by the way, because we're talking about isotropic materials, so fibers are discarded. However, if we have to model any isotropic material, we have to know how does S depends on F. And this is the thing I want to do now. So, for this, assume that W of I1, I2, I3 is given, and find the components Sij with respect to the components of the gradient of the formation Fij. Once again, why is this important? Because in experiments we will plot these components versus these, And in this way, we will reconstruct the energy. So you see how beautiful. There is a way to say in French, and Michel will be very good at telling it in properly, but you can ask him, when you meet him, ask him, tout se tient, which means that everything is holding together nicely. So you see, we're not doing any single useless effort, because we have introduced this energy. I just told you that this energy, how is reduced from 9 to 3, and now I'm telling you how stress is expressed in terms of F. And when you will start next lecture with Michel, you will really see how this is done in real experiments for real materials. It is absolutely beautiful part, and in fact this will be the last part of the theory, and then we will be ready to start with applications. Okay, so let me put ends on the definitions, and let's start to compute. So first of all, we have that stress as Ij is the derivative of W relative to Fji, but W is a function of the three invariants. So this can be broken down as the W in the I1 times the derivative of I1 in the Fij, in Fjy, plus the derivative of W with respect to I2 times the derivative of I2 with respect to Fji. There's nothing strange in all these, yes? Fji is just one variable. W in derivative with respect I3 times the derivative of I3 relative to Fji. Now, of course, you see in this expression, these three guys, this guy, and this guy, these are fully general. They will be essentially the objects that you obtain through curve fitting. But what we instead can and will now compute is precisely the derivative of the three scalar invariants with respect to the components of the gradient of deformation. Let's dive into it. Okay, the first thing I want to do is to compute the first of such guys, which is the derivative of the first invariant of C relative to Fji. Now, so let me write. So first thing, derivative of I1, which is equal to the trace of C with respect to Fji. Okay, let's do it. You will see it is it's not complicated. It's just we have to remember what the trace of C is. So first of all, I just want to remind you, I1 is equal to, well, is the trace of C, yes, but it can be written as the sum for K that goes from 1 to 3 of C, K, K. Yeah, it's just the sum of the guys, of the elements sitting on the diagonal. And I also remind you that C, K, K is actually equal to, well, this is equal to F, L, K, F, L, K with sums in L. So in other words, this I1 here can be written as the sum for K goes from 1 to 3 and the sum of L that goes from 1 to 3 of F, L, K, F, L, K. Now, you may have seen these already with Michel, but in practical situations, to avoid cumbersome notations, you just suppress the two sum symbols. So in other words, these two, for simplicity, you omit them, can be omitted, which means that the you will of course understand that if there is no sum, there is a summation going on. Okay, so the first invariant can be simply written as F, L, K, F, L, K. Since there is no sum, it is intended that L, K are summed from 1 to 3. So this also takes the name of Einstein convention. Apparently it's due to Einstein. Okay, so let's pass to the important thing. We have to differentiate with respect to ij. Let's do it. So we have continued. Okay, let's compute. So first of all, I want to compute the partial derivative of I1 relative to fji. What is this equal to? Well, again, it's the derivative of fji of, I did it, flk. Now, what is the important thing here that you have to understand? You have to remember that it is lk have to be summed. Now, you see, this is the derivative of the same function, so it takes a second to see that this is nothing but twice flk times the derivative of flk with respect to fji. Now, what is this equal to? Well, clearly, when we are differentiating these variable, it's as if I'm doing the, for example, derivative of x with respect to y. So this is an independent variable and this is another independent variable. So you see, the only possibility that this derivative here is equal to, I want to make, just let me be even more clear. Essentially, the tensor f has nine variables. You could call them, just let me call them in this way, just for the sake of clarity. Let me say x, y, z, w, v, t, s, l, g, whatever. So, you see, these are all independent variables. So you see, what it means essentially is that if I, for example, do the derivative of x relative to x, well, this is clearly equal to 1. But if, for example, I do, I don't know, the derivative of y relative to g, but this is equal to 0, yes? It's because they are independent functions. So you understand that this expression here, it will be equal to 1 only in the case where L is equal to J and K is equal to I. You agree with me, yes? Because if this is equal to this and this is equal to this, then it means that this variable is really this variable and then this guy is equal to 1. In all other cases, this is equal to 0. So for this reason, we can say that this is equal to 2FLK and then the Kronecker delta LJ and then the Kronecker delta Ki. Of course, K and I, they're symmetric, so you could transpose. So, what did we find, essentially? Well, let me just recopy here this result below. So I just obtained that this is equal to, well, 2F. Now, you see what it is written here? This expression tells you that this delta tells you that this expression is always a 0 as long as L is different than J. But when L is equal to J, then this expression is not 0. And likewise, K has to be equal to I. In all other cases, if K is different than Y and L is different than J, this guy is equal to 0. You have to sum here, yes? Don't forget, behind this, there is the summation for L and K ranging from 1 to 3. Don't forget that. Well, but what we're saying is that if there is a Kronecker delta Lij, this has to be equal to J, and this has to be equal to 1. It's the only case in which this guy is different than 0. So what do we find? We find that this is equal to, instead of putting L, I put J, so I obtain 2Fj, and here, instead of putting K, I put I. So what is this? Well, this is 2ji. So what is this expression? Fji, what is it, Fji? Well, if you think about it, Fji is essentially the ij component of F transpose, yes? So this is equal to 2 times the component of F transpose ij. let's keep this result in mind. I want to add it in the end. So we found that the derivative of I1 relative to fji is equal to this. Let me box this expression, which will be important at the end, okay? So I discovered, what is this equal to? Now you will see that all the rest is very easy. Okay, so we're done with the first invariant. Let's pass to the second invariant. So we have the derivative of the second invariant relative to fji. What is this equal to? Okay, well, before doing that, I do need to remind you what is the second invariant. The second invariant is 1/2 of, well, we did it. It's the trace of c squared minus the trace of c squared. Yes. So let's how do we express this expression here? Well, in fact, I just want you to remember that we have that this is equal to 1/2 of, now the trace of c squared, what is this guy? Well, the trace of c is I1. So this is nothing but I1 squared, right? And then I get minus the trace of c squared. Okay, so at this point I should do all the calculation, but really I don't want to bore you with this calculation. I will just, but I want you to try to do this calculation. So I omit it because I don't want to enter too much into the details. Do it, okay? Please do this little calculation, not difficult. You see, we have to do the derivative of I1, but we did it already there. And then the only new thing that you have to do is the derivative of this guy, which is not difficult because it is just very similar to this, just with the L and K switched, okay? So just do it and think about it. Think a little bit about it, and you will find it very quickly. What is this? So, well, when we do this calculation, we actually obtain that this is equal to, and this is the thing I would like you to prove, this is equal to the ij component of the following tensor. 2 I1 is just a scalar, F transpose, and then minus 2 F transpose, F transpose, Ij. So it's very similar to what I found previously, but when I compute these invariants, this is equal to, so the derivative of the second invariant with respect to Ji is equal to the Ij component of this beautiful tensor. That is beautiful, I think there is no doubt, but still I can tell you it's not a difficult proof. It's just straightforward. It comes from exactly what we did above, and that's all for the second invariant. So we're almost there. You will see this will be very important in a while. Now the third and last part is in fact the derivative of the third invariant relative to fji. We need all these three items. Now what is this? Well, I just remind you that the third invariant is the determinant of c, which by the way is nothing but the determinant of f squared. Now I'm not doing the proof of this part because, by the way, you will do these in the tutorial. So I want you to do it, yes. In the tutorial you will do this, and you will do, I want you to try to do this, to do it yourself, not to try, do it yourself, and this part will be done in the tutorial. By the way, this is an important result, which probably you may have even encountered in other parts of the course, is called Jacobi's theorem. Now the Jacobi's theorem is essentially, it's telling you how to compute the derivative of a determinant. So you may well have seen these in other parts of the course, but when you do your little calculations here, which by the way it's not complicated, you obtain that these, so the derivative of A3 relative to Ji is equal to the Ij component of the tensor 2i3 f minus 1. the component ij. So this is equal to the derivative of I3 relative to fji. And I want to box also this expression. Now, having all these three expressions of the derivative of the first invariant, the derivative of the second invariant, and the derivative of the third invariant with respect to fij to fji, we can finally determine the components of the stress with respect to the deformation. Let me do it. I want to copy these three boxed expressions in the next page, so you have them in front of your eye, and you believe to me. Okay, well, I've just copied the three expressions from the previous page, and what I want to do now is really to determine the stress, yes? So I want to find what is the Euler-Kirchhoff stress inside of the material. How do I find it? Well, I just remember that to find the stress, we remember that Sij is equal to the derivative of the energy with respect to Fji. And we have seen already. Now, instead of using the... okay, but let me just copy, okay? Let me do it. Derivative of W1 with respect to these, and then the derivative of this guy with respect to Ji, plus the derivative of these relative to I2 times the derivative of I2 relative to Fji, plus the derivative of W relative to I3, and then the derivative of I3 relative to Fji, right? Now, from now onwards, to simplify, let me call this function W1. W1 means derivative of W relative to the first invariant. This I call it W2, and this I call it W3. So what did I find? Well, just let me replace the findings through the three boxed expressions above. Essentially, I get that Sij, just a little bit below. So the component Sij, this will be fundamental, yes? These expressions, we will use them a lot. In all the exercises we will do, inflation of a balloon, torsion of a cylinder, electroactive membrane, bending of something, bending of a block, all these expressions, they will all be based on the expression that I'm about to write now. So what did we find? Well, okay, Sij is equal to, well, first of all, there is W1, so we get W1, and then I have to write the component that I found here, so this is equal to, so you see, I just want you to notice one thing. You see, the Ij component, okay, let me do it one passage at a time. So there would be 2, and then there is the component F transpose Ij. And then I have plus W2 that factors all that beautiful tensor there, 2 I1 F transpose minus 2 F transpose F transpose component Ij. And then there is plus W3 times the derivative of the last guy, which is equal to the Ij component of this beautiful guy here. 2Ij, or girl, what you prefer, this Ij. Okay, so what did we find? We found essentially that the Ij component of this tensor, the stress, is the Ij component of this, the Ij component of this, or the Ij component of this. So essentially, what did we find? Well, we just found that the whole tensor here, the general tensor that is written here S, is equal to the general tensor that is written on the right-hand side. In other words, we finally determined what we wanted to find. That is the general form of S. This would be equal to 2W1 F transpose plus, let me collect the 2 W2 I1 F transpose minus F transpose F transpose plus 2 W3 I3 times F minus 1. My friends, these, for how, let me say, painful it has been? It is the generalization of the Hooke's law, the F equal kx, that you holds for a single spring. For a one-dimensional spring, what would you write for a one-dimensional spring? For a one-dimensional spring, you would write in 1D, you would write that you have a spring, you compress a spring with a force F, or you pull a spring with a force F. Let me say F, and you have a spring, and the spring has an elongation this, and this is F equal kx. Well, when you pass to 3 dimensions, the generalization of Hooke's law is the beast that you see in this green table. So in 3 dimensions, when you have a body, you take a little cube inside of the body, you deform this cube in a certain way, and you have your cube deformed, and the energy, the stress. This is, by the way, something which holds in a single point, yes, because the gradient of deformation will change from point to point. So in each point of the body, the constitutive equation that you see here relates the state of stress to the state of deformation. The expression that you see in this form takes the name of Hooke's law for hyperelastic materials. And it tells you what is the relation of the stress S. Establishes a relation between the stress S and the deformation F in a hyperelastic and isotropic material. It's absolutely fundamental. Something we would wish to do is, in fact, to express. Now, you've already seen with Michel that the formulation of equilibrium equations can be written both in a Lagrangian format, which means through the Piola-Kirchhoff stress, and in a Eulerian format, which means through the so-called Cauchy stress. So the last step we need to do, in fact, is to now see how does sigma, which means the Cauchy stress, relates to the gradient of deformation. I know this part is not really, I mean, of course, it is interesting because we are finding very, very useful tools. I can tell you that these tools, we use them each day in the theory of elasticity. However, I understand it's a bit of, there are some passages which are not so fantastic, but still we need to do them. So I need to do this very last part, which means to relate the Cauchy stress to the gradient of deformation. Let me do it in the next slide. So what I want to do here, the very last part, is relations between the Cauchy stress sigma and the deformation F. How do we do? Well, in fact, it's very trivial. So first thing I've done, I copied the expression of the Piola-Kirchhoff we obtained in the previous slide, and all I need to do to deduce the Cauchy stress is simply to remind you that the relation between S and sigma is simply S equal to J, which means the determinant of F minus 1 sigma. So from this expression, if I invert this expression, I just remind you that this is the determinant of F, usually denoted in this way. So from this expression, I get that sigma is equal to J to power minus 1, and then I have to pre-multiply times F. So it becomes F S, yes? And if you remember that J is actually equal to the determinant of F, but this is actually the square root of the determinant of C, then if you want, this expression could be also rewritten as I3 to the power minus 1/2 Fs. So how do we deduce then the dependence of the Cauchy stress on the gradient of deformation? Well, we simply take this expression here and we use it in the very last I got. And this gives you that sigma is equal to, well, let's just do it in reverse order, and you will see why in the end. So when I factor these times, so there is f times f minus 1, this gives you identity. So there is the first term, which is 2 I3 to the power 1/2, and then W3 times identity. Just let me stress these are tensors, so let me just put a little wiggle below. And then I just leave you to check. This is equal to 2 W1 I3 to the power minus 1/2 times, and then there would be F transpose F, which is actually B. So, and finally the last term plus 2 I3 to the power minus 1/2. And here we get I1, and in fact we get here B. I'll leave you to check this. It's not complicated, and here we get B squared. So if you want, we can this expression can actually be in these expressions here, the tensor B is nothing but the left Cauchy green tensor F transpose. Okay, I'm using a little wiggle just to avoid confusion between the identity and the third and the invariants. So all this in mind, if you want, this expression can be further written in a more compact way, just writing it as follows. And in fact, it is very interesting to find that the Cauchy stress is equal to a certain function of the energy, which classically called B naught times the identity, plus a second function of the strain energy times the Cauchy green, the left Cauchy green tensor, and a third function of the energy that factors B squared. Okay, and these three functions can be easily deduced by the expression above, and the three functions where B naught is equal to 2 I3 power 1/2 times W3 and then beta 1 is equal to 2 I3 to the power minus 1/2, and then W1 plus I1 W2, and finally beta 3 equals to minus 2 I3 W2. Now, minus 1/2. I, of course, as you see, I've skipped the calculations. The somewhat very trivial is just based on the fact that you of what we had obtained in the previous page. But what it is important here, really, I rather want to focus on the physical aspects of what we're doing here. Essentially, we are deducing relations between sigma and the deformation, and it is very interesting to discover that the Cauchy green tensor is not directly dependent on F. So you see, sigma is in fact a function, if you want, of B. Yeah, this is rather interesting because if you remember, the Cauchy green tensor B is a tensor that lives only on the current configurations. It's what is called the Eulerian tensor. So this is an interesting way to express the dependence of the stress, of the state of stress in the current configuration, because there are many situations in which you want to work completely in the current configuration. For example, I can anticipate that in fluids there is no reference configuration, and for this reason there is only the configuration that you are observing. For this reason, in fluids it is usual to employ expressions of the following type. I don't know if you have ever heard of the so-called Navier-Stokes equations. Well, Navier-Stokes equations refer to the behavior of viscous fluids, and in fact in those fluids the stress, the state of stress is defined on the current configuration. Of course, in fluids things become more complicated because since there is no reference configuration, the energy cannot depend on a deformation, but it will depend on the velocity. But this is just to highlight the importance of working in a current configuration. Something I just want to mention is that the tensor B, just let me do a little remark. The tensor B through the Cayley-Hamilton theorem, you could rewrite the term B squared as a function of B minus 1. If you want to see that, it's rather easy, because if, for example, you write the Cayley-Hamilton theorem for B, this would give you that B has to satisfy B cube minus the first invariant of B times B squared, plus the second invariant of B times B minus the third invariant of B times identity. And from this expression, if you pre-multiply everything, you compose this expression with B minus 1. So you just have to compose the whole of this expression. You compose it, since this is equal to 0, you can compose it with whatever you like. It's enough that it's not 0. You pre-compose with B minus 1. Then you see this expression gives you that, well, these first two, they become B squared, and then there is minus I1B, and then there is plus I2. Now this becomes identity, and this becomes I3 times B minus 1, but then I can do equal to I3 B minus 1. So you see from this expression, you see that you could write B squared as a function of B minus 1, B and identity. And for this reason, you could write an alternative form of this expression here. So instead of writing star, there is an alternative form of star, where instead of using B squared, you use B minus 1. And in this perspective, you get the constitutive equation that for coherence you will still use green. This becomes sigma equal to, now there will be different functions, and the expressions of which I will not report. They're written on the notes, they're written on the typed notes that I will upload tomorrow. But these becomes chi naught times identity plus, let's say, chi1 times B, and then there will be in any case a function that it's normally called chi minus 1 that factors B minus 1. Okay, so you see we have essentially two expressions in which the Cauchy stress is depending on the state of deformation in the current configuration, and in one case you see that the Cauchy stress is expressed as a, you see this is fully general, the functions B0, B1, B2 in this case depend on the energy. Also in this case the functions chi0, chi1, chi minus 1, they also depend on the energy. But it is interesting to see that sigma is in a certain sense a combination of these three tensors. Okay, and this holds for all isotropic and hyperelastic materials. So this, it is we remark that these are called representations in fact theorems for isotropic and hyper elastic materials. Now, with this in mind, you could virtually proceed to the curve fitting and on the basis of a specific experiment that you're doing, fit the energy and find the energy, which is in fact the very last step of all the journey we've done in the theoretical nonlinear elasticity course. Now, the very last thing I want to discuss is really something that we will use a lot in the applications. So maybe I just ask you for a little bit of patience with this, I would say, a bit technical lecture, but in fact, I don't think it was difficult materials, just some passage that you, in any case, we will be using this material over and over, so don't worry, because we will learn these things by doing. The last thing I want to do is relation sigma with respect to B for energies that are not written in terms of invariance, but rather written in terms of the principal stretches. You remember we said that at the end of last lecture, and we've used this throughout this lecture, that the energy should be a symmetric function of lambda 1, lambda 2, lambda 3. So what happens if imagine instead of taking an energy that depends on the invariance, you take an energy that depends on the stretches, then how do we write this sigma of B? Well, the first thing I want to do is simply to rewrite the expression I obtained previously, so which was the following: beta naught I plus, well, it's useless to use this, so plus beta 1 B plus beta 2 B squared. Something interesting here is that imagine we are sitting in the system, in the reference frame, in the local reference made of the eigenvalues of B. In this system, B as eigenvalues of course lambda 1, lambda 2, lambda 3 squared, and eigenvectors v1, v2, v3. So let me sit inside of this specific system. So you see what happens here. Imagine we write it from the hand, but I won't anticipate. This is just a diagonal tensor, so 1, 1, 1. These will have lambda 1 squared, lambda 1 squared, lambda 1 squared, and everything 0. And also this guy will just be exactly like this. It will have exactly the same eigenvalues, but instead there will be lambda 1, 4, lambda 2, 4, lambda 3, 4, and all the rest 0. What does this mean? This means actually that the reference in which B has principal directions v1, v2, v3, then it means that v1, v2, v3 are also eigenvectors of sigma. Because you see, this is an identity, this is a diagonal, this is a diagonal. So the sum of 3 diagonal tensors will have to be a diagonal tensor. So in other words, we find that sigma is diagonal in the reference made of the eigenvectors of B. And if I want to write this in a matrix form, this becomes, well, this will be the first component of sigmas, which means the sigma 1, 1, 0, 0, 0, sigma G2, 0, 0, 0, sigma 3, 3. Now this is equal to what? Well, let me write the 3 expressions that are written above there. We have beta naught, and here you have the 1, 0, 0, 0, 1, 0, 0, 0, 1. So this is the first piece, beta naught times the identity. Then there is plus beta 1. Also this guy is the one I was telling you before. So we have lambda 1 squared, 0, 0, 0, lambda 2 squared, 0, 0, 0, lambda 3 squared. So this would be the B guy. Let me just displace it a little bit here. Okay, good. So finally, the third and last term, this becomes beta 2. And here we have lambda 1 to the fourth, 0, 0, 0, lambda 2 to the fourth, 0, 0, 0, lambda 3 to the fourth power. Now, if I want to find from this expression sigma 1, 1, you see, it is absolutely easy, because we immediately find that sigma 1, 1 is equal to, well, beta naught, then there is plus beta 1 lambda 1 squared plus beta 2 lambda 1 to the fourth power. And likewise for all the other components, sigma 2, 2 would be with 2, sigma 3, 3 with 3. Now, if instead of taking, and I don't do it really, I don't want to abuse your patience, but if instead of this beta naught, beta 1, beta 2, you write the definitions in terms of energy, and you write the definition in terms of energy that we have already written in the past, in the previous page, you find that this is actually equal to 2j minus 1 lambda 1, and the derivative of the energy when this is expressed as a function of lambda 1, lambda 2, lambda 3. So let me put a little wiggle on top, or let me just put a little hat on top to say that this energy, I'm using an energy which is expressed in terms of the eigen values instead of being expressed in terms of the invariants, differentiated with respect to lambda 1, which is rather very simple. And I leave you to do the proof. Also, these I leave as an exercise. Do it. It's not difficult, but really this is the last thing, the last 2 lines of this lecture. It's simply I'm writing the same expressions for 2, 2. So if you do the same for sigma 2, 2, you will obtain that this is equal to 2j minus 1 lambda 2 derivative of the energy expressed in terms of the stretches relative to lambda 2, and sigma 3, 3 likewise equal to, you can prove it, but it's enough in fact to prove it for 1, and this is equal to 2j minus 1 lambda 3 derivative of this energy relative to lambda 3. You may say this was much more simple, but in fact to get here we in any case have to pass from the invariants, and don't forget this was important to get all the structure leading to the Piola-Kirchhoff stress, to the nominal stress tensor S, and then from there we understand how is the Cauchy stress done, and you see it's all a work in progress that led us here. Okay, I think with these I will just conclude this lecture. It was I have to say probably not immediately. I don't think there is any intrinsic complexity of what we have done. But if you want to see, let me see, to understand what you did, this is all we did, is just the generalization of Hooke's law, F equal to K delta elongation in 1 dimension. Well, we did a little bit of passages to get to the relation between sigma as a function of, let me just say, a certain function of the deformation. Yeah, so in the passage between 1 dimension and 3 dimensions was really the goal of these lectures. I now will close this part, and I will leave you in the good hands of Michel, with whom you will start to play on concrete problems. And we will see each other again in the very last part of this course, where hopefully we will still be doing very nice examples. I wish you a nice week. I am recording these things already in the weekend, so you can have all the lectures at the beginnings of the week, and you can decide when to watch them. And I will also upload my typed lectures later today. Okay, have a wonderful rest of the week. Bye bye, my friends.